Okay, I just showed you how to do Faraday's law for average EMF. Now I'd like to show you how you use the top equation. Remember the EMF that's induced in a hoop, the voltage in other words. And by the way, if you know the voltage and you know the resistance, you can get the current. But the EMF that's induced in a hoop is just going to be how fast the flux changes with time. The derivative of phi with respect to time, the negative derivative. So let me show you how that applies. Here we have a setup. The dots; those are red. Those are orange dots, and they're coming out at us. And this is just a wire, 10 centimeters. Another 10 centimeter wire, another 10 centimeter wire, another 10 centimeter wire. This is hollow. That's just air. Okay. Now I want to make a point here. That's not a small point. This is actually a pretty big point, and that is that this field, while it's not constant, it's changing with time. See, at t equals 0, there is no field, but at t equals 1 second, if I put in 1 there, I get 5 Teslas. And if I put in 2 seconds, I get 20 Teslas. It's increasing pretty fast. But while this is changing with time, it is a uniform field, meaning that the field is the same at every point. I'm just going to tell you the field is the same here, is here, is here, is there, is there. So the field itself is uniform, even though the field at any given time will be different. So let me say that again, because this is no small point. At 1 second, it's 5 Teslas, but it's 5 Teslas everywhere. So that's why I'm saying the field is always uniform, but it's not constant. It's changing with time. And that's going to matter when we go to do this, because if I want to know the EMF that's induced, it's going to be the EMF that's induced is the negative the negative derivative. I don't know why I wrote that in there. The negative derivative of the magnetic field flux with respect to time. Okay, so before I can take the derivative of the flux with respect to time, I need to actually get the flux. So I'm going to first find this. I'm going to find the circled thing. And once I do that, then I'll take the derivative. Okay, so the magnetic flux is going to be equal to the integral of B dot dA. Now, the dAs, let me draw you one dA for this hoop. It might look like this. Now, dAs are really small, but I'm going to make it big enough so you can see. And let's say that's coming out at us. So you see B and dA are always in the same direction. So I can get rid of the dot product, because the dot product says take the part of B that's in the direction of dA and multiply it by dA. That's what the dot product does. It takes the part of B, the component of B, that's in the direction of dA, and it multiplies it by dA. Well, if I do that, that's just going to give me B times dA. Okay, now B is the same at all locations. And so because it's the same at all locations, I can pull it out of the integral. Now, you might say, well, wait a second, isn't it changing with time? And you'd be right. The B is not constant, but it is uniform. If this were a dt instead of a dA, I would not be able to pull that B out of the integral. But because it's a dA, that means that that's with respect to location. And so as long as the B doesn't change with location, meaning that it's uniform, then I can pull it out of the integral. So then when I do that, I just have B times, when I add all those up, just B times A, which is often what you get when you're figuring out flux. Often, but definitely not all the time. So if I do that, then I'll just do B, which is 5 Teslas over second squared times t squared, times A. And A is going to be just 10 centimeters by 10 centimeters. Remember, let's be in the MKS system, so that's going to be 0.1 meters times 0.1 meters, which is going to give us 0.01 square meters. Okay, so that's going to be, if I pretty this up a little bit, 0.05 Teslas over second squared meter squared times meter squared times t squared. That is our flux. Now, remember, I've only found the flux. I have not taken the derivative of it yet. So to get the EMF, I'm now going to take the derivative of the negative derivative of the flux with respect to time. So that would be this. Now when I do that, I get that it's equal to the negative. You know, this negative sign we will take care of in actually the next video. We'll use something called Lenz's law to tell us the direction of the current. So I will rarely use that negative sign, but I'll always pull it along so that the math works out. Okay, so if I take this derivative then, I'm going to get 0.1 Teslas second squared meters squared t to the first power. Okay, so apparently this voltage, this voltage is changing with time. So at t equals 0, there is no voltage. But at t equals 1 second, I'll get 1.1 volts, negative 0.1 volts. Excuse me. At 2 seconds, I'll get negative 0.2 volts. So apparently the voltage, not only is there a voltage induced, but it's changing with time. Okay, so to just reiterate, what you have to do is you have to find your formula for flux first, your expression for flux, and then take the derivative. And usually the derivatives are very straightforward. Okay, now it turns out that what happens if you have more than one hoop? Well, that's no problem. You're just going to put an n here for the amount of hoops you have. So it's the same equation, but if you have 500 hoops, then you get 500 times more of the EMF that's induced, the voltage that's induced. So that's why I put that n in there in the first place the last time, is because I was thinking of this equation when you have more than one loop. Okay, now to be fair, this is the entire Faraday's law, and I'm going to explain this in another video. But it's saying that the EMF induced is equal to the rate at which the flux changes, the negative rate at which the flux changes in the Faradian loop. But it's also equal to the integral, the closed loop integral of E dot dl. Just so you know that there's more to, a little bit more to it, and I will explain that in a future video. Okay, so to induce a current in a hoop of wire, you need to change the flux. That's what you need to do. You have to change the flux. And this is our equation for flux. So to summarize all this and put it in just some simple terms here. If you want to induce a current in a loop, or induce some voltage in a loop, you'll need to change the flux. And here are the ways you can change the flux. You can either increase or decrease B, you can increase or decrease A, or you can change the orientation at which A and B are at with respect to one another. You can take advantage of the dot product. Okay, let me just say that for number one, how would you increase or decrease B? Well, you see this loop of wire? It's got some flux. Oh, it has some flux through it. I could, just by changing the current in here, change the flux. And by changing the current, I could change the flux and induce a current around here. I could also change the flux I could also change the field in here by just moving it this way. If I moved it this way, that's going to make the field less. If I move it closer, it'll make it more. But if I move it this way, it won't change the flux. And if I move it that way, it won't change the flux. Okay, how would you change the area? Well, you could take this, if this were expandable, and you could just, if it was like rubber, like a rubber metallic substance, I don't know how, but you could increase the area that way, I suppose. But here's another way you could do it. You could take, this is a metal wire that goes out for a long way. Now we don't have a hoop, but what if I put a slidable piece of metal here, like a trombone thing, and I just slid this along? Wouldn't the area of our hoop, the effective area, be getting bigger? That's another way to change the area.